In this presentation, I'll be discussing a JPEG decoding accelerator built for the course ECE5775, high-level digital design automation, with Ahmed, Yash, myself, and Yassine. So JPEG is becoming pretty important in the modern world. Billions of images are shared daily across devices, and JPEG is the most common format of these images. And it's necessary, or the decoding and encoding stage is necessary for every image load on computers and smartphones and other devices. And this is even true for video loads as well, where a lot of the similar components are shared between JPEG and the most common video formats. And even modern image classification tasks, for example, are run on the majority of images sent by popular messaging services and by cloud backups. And what we have here is a quick early study on the percentage of time dedicated to the image load process. So this is shown in red, and this image load process is dominated by the JPEG decoding stage. So what you see is as the resolution of the image increases, the time spent on the image loading and decoding stage eventually dominates the entire time for the image classification task. So the JPEG algorithm itself is designed to minimize the informations that humans cannot easily perceive. So it does this by downsampling the amount of information, especially in the color domain, and it gets rid of the high frequency changes in lighting. So for example, when this image, which is compressed using JPEG, very heavily compressed using JPEG, you can see that the mountains turn into these jagged lines because it has removed all the high frequency data and just left the low frequency data. And in the next few slides, I'll be describing the encoding process, but the decoding process, which we focus on accelerating, is just the inverse. And the key components of these processes are the discrete cosine transform, quantization, and entropy coding. The discrete cosine transform takes the image and divides it into 8x8 patches and applies the transform to each of these patches. And the main purpose of this transform is to transform from the spatial domain into the frequency domain. And in this frequency domain, where each of these squares represents an individual two-dimensional sinusoid, individual frequency, the DCT gives it a frequency weighting, which is SVU. And then in order to reconstruct the original image, you do the inverse discrete cosine transform and use these SVU terms with a bunch of other terms, and then do a double sum, and then this reconstructs the original spatial image. So we're focusing on accelerating the IDCT since we're doing JPEG decoding. And after you have the frequency weights for the image, the next step is quantization. So this involves a division by a pre-known quantization matrix and then rounding. And the importance of quantization is to reduce the number of bits used for each number, and also it induces more sparsity, which will be taken advantage of in the next stage. And this stage in entropy decoding, it takes the sparse quantized frequency weights, it runs it through a particular zigzag linearization process. So this will take -30 to 5, 0, 0, 0, and it goes through the matrix in a zigzag way. And then this process is designed to put many of the zeros, or at least the coordinates that are most likely to be 0, next to each other in the vector representation. And then the run length encoding will go through and then combine these adjacent zeros together into a single list. So here there's a 6 here. So this column represents the number of zeros for each term. There are 6 because there are 6 zeros in the original matrix here. And then it's finally passed through a Huffman compression, which just uses variable length bit widths in order to represent the most frequent terms with the smallest representation, and the least frequent terms, so for example, this -30 here, with the largest representation. And then finally, these are all concatenated together and then zipped up into the JPEG format. So now shifting from the description of the algorithm to our results, we'll first discuss the synthesizable baseline. To create this, we referenced an existing C++ implementation online. However, this contains data structures such as hash tables that cannot be easily synthesized, and they must be replaced with structures that could be used directly with HLS. This baseline includes run length decoding, the zigzag reconstruction, dequantization, IDC, and some post-processing functions. And you can see here that the max latency is 23 million cycles to begin. Our first optimization was to replace the complex mathematical functions in the IDCT transform. And so first we focused on the cosine function itself. This one can be synthesized, as we've seen in previous labs with Cordic, but using a pre-calculated table is much faster. And in this case, since we're operating on only 8x8 blocks, this requires only 8 unique cosine values. And then we replaced the square root within the IDCT with a constant value, and we converted the rounding function to an arithmetic expression, as shown here. This immediately gives a 71 times speed up over the previous max latency and decreases the resources across the board. Next, we handled the data types. So the baseline by default uses floating point multiplication and data. However, these are resource intensive within HLS. So we converted these floating point types into fixed point types, which have less precision but offer better performance in terms of latency and resource utilization. And we also converted other variables to low precision types when we had hard guarantees on the upper and lower bounds that they could take on. An example are the loop variables, which we also converted to low precision data types. And overall, this gave another 2.7 times speed up in terms of latency and decreased the resources across all categories. Next, we applied further Vivado directives. We included pipelining, unrolling, and array partitioning. So for pipelining, we were able to increase the performance by leveraging the parallelism in the design. The trade-off here is that we can squeeze more operations into a single cycle, yet this incurs higher resource utilization. And equivalently with array partitioning, we're able to split the BREM into multiple arrays, effectively increasing the number of ports and concurrent reads and writes. However, this also leads to more resources. So here, we achieve an additional 16.8 times speed up over the previous step, but a very large increase on the board resources. Finally, we restructured the IDCT code to split the loop nest into two different parts. And so these two parts, the first one computes an intermediate table, and then the second one uses this intermediate table's values to compute the final IDCT scores. And this gives better performance through harder pipelining and parallelization, yet it gives lower accuracy because we store the intermediate results in a lower precision. And for one of these loop nests, we additionally split that operation into multiple parts and introduce an intermediate variable. And this shortens the dependency cycle and allows a better II. And with this optimization, we achieve an additional 3.4 times speed up over the previous step, and especially increase flip-flops and the lookup tables. Yet all the resources are still within the Z-board's bounds. So all these optimizations in summary are listed in this table with the different steps on the y-axis here. And this column lists the speed up relative to the previous row. So overall, the math function conversion, primarily the cosine conversion, had the largest speed up with 71 times over the baseline. And the extra Vivado directives also had a large speed up with 17 times over the previous steps. And overall, our accelerator is 10 times faster than our ARM CPU baseline, with the accelerator coming in at 9.4 milliseconds versus 95.9 milliseconds.